Expectation value of an operator. Expectation value of an operator, or say expectation value simply. How we define the expectation value uh, in quantum mechanics. In general, what we do, if we choose a random variable, if we choose some random variable, say q, which can take values, in the set, say q1, q2, q3, so on, qn. With the probabilities say p1, p2, p3, and so on, pn, then statistically we define the expectation value of this random variable q like this. This is defined by this angular bracket. This is expectation value of this random variable q, as if we sum over all the values, sum I is equal to 1 to n, qi multiplied by their corresponding probabilities. So this is how we define the expectation value in statistics for any random variable which can take certain values with their probabilities p1, p2, p3, pn. This random variables q could be anything, like it could be head or tail or dice, number of the dice, 1 2 3 4 5 6, anything which has a certain probability of arising. But in quantum system, in quantum system, what we do is, let us take an example that uh, the expectation value uh, the expectation value of x, so this is my x, this is the position of a particle, confined to x-axis, uh, and that is described by the wave function psi, this is psi xt. Okay, so in quantum system we can define the expectation value of position for a particle is like x is equal to, because here we replace the summation to the integration, because everything is integrate over, and this, because this is a value of the random variables. So value of x, whatever will be the value of x, we put here, and then multiplied by the probability pi. Okay, the probability of x. So what will be the probability of x? We know it. This will be psi star xt, psi xt, and dx. So this you know already, this quantity. What is this thing? This is nothing but, we can write it, this is x mod psi square dx. Okay, so this is the probability. This is probability density. This is probability density. So the number multiplied by the probability density of that particular variable x. Fine. So this is what this is giving you the probability of finding uh, the particle uh, in the region x and x plus dx. Okay, x plus dx. So this is how we define the expectation value of any variable or observable in quantum system. And what it actually means experimentally, that uh, this is some mathematical expression. Experimentally, what does it mean actually? Experimentally, what it means that if we make many copies of this state psi, this is state psi, this is a state which is defining the position of the particle. So if we make many hundred and thousand copies of such states and try to measure the position of that particle for all these states at the same time, and the average value will come out to be equal to the expectation value of this position x. This is what we experimentally means. This quantity may be time dependent, may be time dependent also. Okay, so in general, we know that expectation value for any quantity, say any quantity dx, can be written as minus infinity to plus infinity, the value of the quantity, and this is multiplied by the probability density integrated over its variable dx. This is how we define the expectation value in quantum mechanics. Operators are another way to find the expectation values. Actually, we have gone through many operators in our calculus class, and we know that an operator tells us what operation to carry out on the quantity that follows it. Okay, for example, if I have a position vector, and if I have a position vector, and if I differentiate it with respect to time, then what I get is the velocity vector. Okay, so d del by del t is an operator, because when it operates on the position vector, this is the quantity which follows it, it gives me the desired quantity, which is the velocity. So del by del t, this is differential operator with respect to time. This we know already. In quantum mechanics, we're going to deal with the momentum operator and the total energy operator. Okay, and then we can have a total kinetic energy operator. So let's start with the free particle wave function. You know already how to write the free particle wave function. This is my psi equal to a some constant e minus I by h cross, and then et minus px. This is my free particle wave function. And now when I differentiate it with respect to x, this psi, what I get is uh, a minus I by h cross et minus px, and then multiplied by ib by h cross. Okay, so this is nothing but I by h cross times p, and then this whole thing is equivalent to psi. This whole thing is equivalent to this psi. So we have del over del x, and then psi is equal to I by h cross p psi. And from here we write this p psi, p psi is equal to h cross by I and del over del x of psi. So from here we can see that we can write the momentum operator. This p as a momentum operator is equal to h cross by I del over del x. Okay, so when this is an operator whose form is h by I and del over del x. When it operates on psi, that means this operates on psi. So this is known as the momentum operator. Momentum operator in quantum mechanics. Similarly, if we differentiate this free particle wave function with respect to time, if I say del over del t of psi, and then I get a minus I, sorry, I over h cross et minus px, and this is multiplied by I e by h cross. So we get del over del t of psi is equal to minus, there will be a minus sign because this is here. This is minus I over h cross and E times psi. So from here I can write E psi equal to I over I, uh, write IH cross, can write IH cross del over del T times psi. Here I have used that I is equal to minus 1 by I. Okay, we can write it. So again, we can write the operator, which is this operator E, and this is equal to IH cross del Y del T. This is an energy operator. When it operates on psi, that means this operates on psi. This is the total energy operator. So this is total energy operator in quantum mechanics. And this hat is symbol for an operator, which is known as caret. This hat is what it is, caret. Okay, so for an operator, we put a caret over the quantity and it becomes an operator. So similarly, we can write, once we have a total energy operator, uh, we can write the kinetic energy operator, because we know that the kinetic energy operator you can write, because will be equal to, because we know this is kinetic energy is p square by 2m. So p is, we know that momentum operator is p square, so we can write this 1 by twice m, and p, we already know p operator is this, so we can write this is h by I del by del x square. So this becomes minus h square by twice m, because I is I square and I square is minus 1. So, and then I have del square by del x square. So this is a kinetic energy operator. So the momentum operator, we can have the total energy operator and the kinetic energy operator. So now we will look for how to write the expectation values for these operators, momentum energy operators. So we can write the expectation value of the momentum operator as say this is expectation value of the momentum operator. So P, I can write is equal to minus infinity to plus infinity, and I can write it as psi star and the momentum operator, and then my psi dx. So this I can is minus infinity to plus infinity, psi star is there, and because the momentum operator is h upon I del by del x, so I put the value of this here. This is h cross by I, this is del by del x, and then psi dx. Okay, so this becomes h cross by I minus infinity to plus infinity, psi star del del x of psi dx. This is how we define the expectation value of momentum operator, or you can delete this operator, or you can say simply the expectation value of momentum. So one thing you can notice that I have not written this P uh, as like P as minus infinity to plus infinity, this P, and then mod psi square. This is what we have, psi psi dx. I have not written this like as earlier in position expectation value. So we cannot write it like this, because if we do this, what will happen? So if I put the value of P from here, so this will be h cross by I, will take outside, minus infinity to plus infinity. This will be del x of psi star psi, okay, dx. And when we do it, this will be h cross by I, and if integrate it, this will be psi star psi minus infinity to plus infinity, which will comes out to be equal to 0. So why? Because psi star and psi must be 0 at extended to infinity. Why 0? Because from if my wave function is normalized, an accepted wave function, then one of the condition is that the the wave function psi must tends to 0, or similarly the psi star will tends to 0 as x, y, or z tends to plus minus infinity. So if we write the expectation value in such manner, then it is not going to give me any physical thing. It is always going to give me the 0. Similarly, if I try to write uh, the expectation value P like this, minus infinity to plus infinity, psi star psi, and then P dx, so what will happen? So I can write h cross by I directly outside. This minus infinity to plus infinity, I'll have psi star psi and then del x of dx, which makes no sense. Which makes no sense. So putting the quantity of which we are finding the expectation value at proper position is very important. So that you don't give any nonsense things or unphysical thing or 0. So in the same way, we can write the expectation value of energy. So this is what we have, is minus infinity to plus infinity. So I can write it psi star energy operator psi and then dx. So this is, you can write minus infinity to plus infinity I psi star and then I h cross del over del t of psi dx. This is IH cross minus infinity to plus infinity psi star del del t of psi dx. So therefore, in general, we can write the expectation value of any quantity which depends upon position or momentum can write as, better to write like this: minus infinity to plus infinity psi star, the value of the operator, and psi dx. So in this way, all the information about a system can be obtained from its wave function psi. Let us consider an example uh, that a particle limited to the x-axis has a wave function psi equal to ax. So if a particle which is limited to move along the x-axis only uh, between x equal to 0 to x is equal to 1, so this is the region where the particle is allowed to move. Okay, and the wave function for this particle psi is given as some constant a times x, and psi else outside this region psi is 0. Fine. So now what we have to find is case A, find the probability that the particle can be found between x.45 and x.55. Okay, so let us make x equal to, let's not take x is equal to 0, and x is equal to uh, half. Forget about this 0.5 and this. So we have to find the probability. Okay, probability of finding the particle which is moving along this x-axis between 0 and 1. So we have to find its probability particle to be found between x is equal to 0 and at x is equal to half, between this region. Okay, so we know that we can find it, the probability between, say this is x1, this is x2, this is x1 x2. We know how to define the probability. This is between x1 and x2. We have to find this mod square psi square and dx. So this we can write as x1 is 0 and x2 is half, and this is psi star psi dx. Okay, so psi is ax. So if I multiply it this by 0 to half psi star, because there is no complex when only real part is there, so this is ax multiplied by ax, and when we have dx, so because a is constant we can take it outside, this is a square, so 0 to half, and then we have x squared dx, this becomes a square, and this is x cubed by 3, and we have 0 to half, and then this is a square, this is 1 by 3, I can take 3 outside, 1 by 3, 1 by 2. Okay, this is 1 by 2 the cube minus 0. So p x1 x2 is a square by 3 multiplied by 1 by 8. So this is 1 by 24 times a square. This is the probability, whatever the constant a divided by 24 is giving you the probability of finding the particle between two position x1 and x2. Similarly, we can find the expectation value of the position, which is like this, and you know how to define it. This is actually from, we have to find from minus infinity to this is plus infinity, and this is how we define. This is x times mod psi square dx. So our limit here is basically not minus infinity to plus infinity. This particle is from 0 to 1. The maximum limit is 0 to 1. So this is 0 to 1. We have x, and this psi square is psi star psi, and we have already defined it. This is a square x. This is a square x square dx. So this you can write x is a square outside. We can add 0 to 1, and this is x cube dx. So this comes out to be a square. This is x4 by 4, x5 by 4 is 0 to 1, and so this is basically a square by 4. So the expectation value of particle is a square by 4. So most probably the particle is expected to found at a square by 4 region in within x is equal to 0 to 1. Now you can also check whether this wave function is normalized or not. If this wave function is, say, it's normalized, then what is the value of a? Okay, if this wave function is normalized, what is a? Okay, so we know that the normalization condition, if we apply the normalization condition that says that minus infinity to plus infinity mod psi square dx must be equal to 1. So if we apply this to here, that is 0 to 1, and this is a square x square dx should be equal to 1, and that implies a square 0 to 1 x square dx, and that implies a square uh, x cubed by 3 0 to 1. So we have a square by 3 is equal to 1. This implies that I'm saying 0 to 1 a square a square x square, and this is 1 by 3, so a square by 3 equal to 1, and so this implies that a is equal to root 3. So a normalized wave function, here we can write this psi normalized is root 3 times x. This is my normalized wave function.